Alright, cool. We're up and running. The All Access Pass, yes. Much coveted. I changed my profile picture. That's a picture of me actually when we were on strike last year. And I was pretty happy because I was walking the picket line. But life was good. How in the world do you save the increment values for maxval, as you recursively call it, when you have a variable amount of items? Good question. Yeah, that was Red for Ed. Excellent. Yeah, and I just had some surgery that greatly improved my life, and I was out walking around, and it was starting to snow, and my girlfriend, now fiance, who was a Teamster before, had come out and was walking the picket line with us, and it was actually a surprisingly good line. Cool, thank you for having been there. That's awesome. Yeah, I'd never done anything like that before, but it was really cool to see students out there. That was great. Let's see. All right, so saving the increment values for maxval. So I assume you're talking about the inventory of items that give you the maximum value. And so we have a variable number of items, but I put a limit on it. I said there's no more than 128 items in your inventory. So you can do a good old statically allocated array, something like, integer items bracket 128, and initialize it to 0. And then the value of items bracket 5 is the number of item 5 that correspond to a particular max value. And so if you make your maxval function, not in the inventory, but the total price as you add the price plus maxval. Yeah, so if you make a structure, I keep calling it answer. And you can't initialize inside a structure, but do something to initialize it. But if you have a structure that contains a count of items and a maximum value, then make your maxval function return that structure. And so inside this function, you've got your for loop. So for each item I, value equals price I plus, well, so do it like this. Call the maxval function first. This is capacity. Capacity minus the weight of item I. Right? So call your maxval function, get back this whole struct answer, and now do your if statement. If temp dot maxval plus price of item I is bigger than best. Right, and if it is, then this is your best answer so far, is to start with item I. So make best a struct answer also. So instead of saying, integer best equals 0, and then if this is better, set best equal to that integer, make best a struct answer. So it includes both the maximum value and the count of items. Right? So make that a local variable inside maxval, initialize it to a maxval of 0 and an item count of 0. And then for each item, right, call your maxval function with the reduced capacity, get the answer back from that, add the value that you got to the price of the item I. If that's better than best dot max val, right, then do something like best equals temp, which will copy the information that you got back from max val, which was an inventory, and the actual max val. And then increment the max val by the price of your item. Or, if you like, temp max val plus price of item I. Right, so just that. And then adjust the inventory, right? So increment best.items bracket I. And that's what takes care of adjusting the inventory count. Right, so this is the magic right here. So have max val return a structure. Use the max val piece of that structure, add your price of your item to it, see if that's better than the max value that you've seen so far, and if it is, copy the answer you got from max val into your local best structure. Set the max val in that best structure equal to, you know, the temp max val plus the price, and then increment the count of item I in that best inventory. So that's incrementing that thing that we were doing on paper. And when you're done with all of this, best will be your final best answer, and just return that. And that should get you. If all we pass to max val is capacity, then how does it have access to the array with the items in the list? So cleanest way, just pass that as another argument. And you're never going to modify that. The all items array is set up when you read the data file, but just pass that into max val and pass it along down here, and just, you know, you can avoid having a global like that. You can make it global if you like, but be careful if you split your file into, if you split your program into more than one file, globals get tricky. You could set this up inside, you know, a global right before your main program. But if your max val function is in a separate file, you have to use an extern keyword to tell it this is a global defined externally, or just put everything in one file, which I think is easier. If you declare it in a main.h file and you include that main.h in multiple files, you're going to confuse the loader. At best, you'll get a compile error. At worst, you'll end up with two different global variables. So declare it right before main and put everything in one file, or best solution, just pass it to max val. Wow, I'm like tall and skinny here. There we go. All right, good. Other questions? Can you go over what the code on that paper does one more time? Yeah. So make yourself a structure which will contain the information that you want to get back from max val, which is an integer maximum value, but also an array of item counts. And the setup is, if you use this array to tell you how many of each item you have, if you add those up, you should get this max val. So if your maximum value comes from, you know, 1 of item 2 and 3 of item 0, then you would, you know, expect your item array to be that: 3 of item 0, 2 of item 2, none of the other items. All right, so that's just a count of items. And then have have your max val return an object of that type of structure. And inside max val, instead of having an integer for your best value you've seen so far, have a struct answer for your best answer you've seen so far. Initialize that. So set max val to 0, set your item counts to 0. And then do your regular for loop where you go through each item and you say, what happens if I start by putting item I in my bag? Well, if you put item I in your bag, then you have a bag with a remaining capacity of cap minus the weight of item I. So call max val to see what the best is that you can get out of that reduced capacity bag, right? And save that in a local variable. I'm just calling it temp. So did that give us a better overall solution? Well, if we started with item I, then we can get temp.maxval out of the rest of the bag. And we also get the value of item I because we've got that sitting in our bag. So this sum is the total value that we can get out of our bag, the best possible total value we can get out of our bag if we started with item I. So see if that's better than the best value we've seen so far. I'm using best to record the best solution that I found so far. So best.maxval will be the maximum value that I've seen up to this point, which you should have initialized to 0. So if this is a better solution, then I want to record that solution in my best variable. So I set best equal to temp, that's the value I got back from maxval. I set the actual value of this best solution to be this calculation up here. The value I got from this call to maxval plus the price of item I. So that's what this does. And then this part, this is the inventory adjustment. If this was the solution for my bag with diminished capacity, my best solution comes from using that solution, but also adding 1 of item I. So I'm going to increment the count of item I in my items array. And so at the end of this if statement, right, best is the complete description of my best solution up to this point. So when you finish the for loop, best will be the best solution of all possibilities. And remember up here, before you do any of this, check the legality of this solution. Make sure that the weight of item I is not bigger than the capacity of the bag. If it is, don't do any of that. Just go back and try the next item. But as long as your item fits in the bag, calculate the max val of that, compare it to your best, save the result, update the inventory, etc. How would the max val function return a value if the max val you found was multiple items? What do you mean by multiple items? Okay, cool. And yeah, functions can return structures just like ints. It kind of works, but make sure it's just a structure, not a pointer to a structure. And your base case is if the capacity is less than or equal to 0. And in that case, you want to return an answer with a max val of 0 and an item count of 0. And if you initialize your best to be, you know, a max val of 0 and an item count of 0, then right here you can put in your base case. And if your capacity is 0, just go ahead and return best, which is currently a bunch of zeros. And you should never end up calling max val with a negative capacity. If it's a negative capacity, it means you called it when the weight was bigger than the capacity, and you should never do that. If capacity is negative in here, you've probably got a programming error somewhere. Would that structure be the data that gets stored in the cache? Yes, so if you want to add caching to this, right, this all becomes that box that I keep drawing. And before you do any of this, right, check your cache bracket cap dot max val, right, or put a flag in here if you like, to see if you've saved that. So your cache is going to be a cache of struct answers, right, and each of the entries in your cache, the struct answer should have a max val of 0 to begin with. So before you do any of this work, you're just coming into your max val function, check your cache bracket cap. If it's got a max val that's not 0, then just go ahead and return cash bracket cap, which will be a struct answer. Otherwise, do all of this at the very end before you return best. Cash bracket cap equals best. That saves it in the cache. And then the next time you'll end up just returning that saved value. I always make my base case cap equal 0. Because you should not end up calling it with a negative value. But if you make your base case less than or equal to 0 and your case is never negative, it's still going to work. It does no harm. You're just checking for, it's like saying if such and such or 1 equals 2. I mean, it's not going to break your code, but technically your base case only has to check to see if the capacity is 0. Cool, good questions. All right, other questions? Max val at the very least needs the capacity. But it's if you don't want to deal with globals, go ahead and pass it the array of items that you read in from your knapsack file. And then you've got access to that inside here, the prices and the weights. I don't like this program. Oh, sorry about that. It will possibly feel better once it's all done and working. It can feel kind of I don't know, a little gnarly maybe when it's got all these different parts and pieces. But you may like it later. Just like college, I can't wait for it to be over. Yeah. That tends to happen sometimes. Honestly, college can be a lot of fun though, in some ways. On the other hand, when it's over and you're working, you're getting paid for your time, and you get weekends off and you get evenings off, and that's kind of nice too. But there's some potential upsides to college too. The stress is not fun. I agree. Yeah, it's definitely different being online. And like I say, I'm pretty hopeful that fall will at least be somewhat in person. And yeah, it's definitely a lot more fun if it's the only thing going on, which it rarely is. But you're getting through it, and that's awesome. And 223, it's a lot harder. It's deeper material. It's more advanced concepts. It's larger projects. But in a lot of ways, 223 is the most fun of these courses, because we've got so much machinery at our disposal, and we're working in Java, and it's object oriented, and we've got all these libraries of things to pull from. And it starts to be a bit more fun to just sort of take things and put them together. That's a t-shirt. Definitely. All right. Any questions on the quizzes? Those quizzes are due tonight, I believe, at midnight. So, and I'm not going to be online later today, so if there's any last minute questions about them, we should go over them now. Yeah, those are all fair game for the final. Any questions about tries? So I don't think we talked full on about trie traversal when we did our quick pass through of tries. the other day. I talked about it in the other section. But this was our sort of basic trie setup. So our nodes, contain 26 pointers and an end of string flag, and by default, all of these pointers are null, just like in a binary tree. If we don't have something pointing somewhere, we just say that that's a null pointer, but we don't usually draw an arrow with the word null. So starting off, all of these things were null, and we added some information into this trie. So, for example, there was a word that started with C, followed by A, followed by T, followed by the end of string. That was the word cat. Right, so start with the first letter, follow that to another node, follow the pointer associated with the second letter, which is A, to a third node, follow the pointer associated with the third letter, which is T, to a fourth node. If that's the end of the string, check the end of string flag. If it's set, then there's a cat stored in here. So we do have a cat. We also had a C pointing to an A, pointing to a B, and that B came down here and there was end of string, so we had a cab. And we had a C pointing to an A with an end of string, so we had plain old California sitting in here. And we had an H pointing down here to an I, pointing to a node with the end of string, so we had the word high. And I think that was all we had stored in our trie. And so if you want to traverse this and find all the words, you can do this with a recursive loop, right? So we could start at the first node, and if this is not null, then we could simply follow that to a node and say traverse everything from that point on down. But everything that you traverse, every word that you find, begins with the letter A. Right, so do your traversal, but anything that you're going to print the letter A in front of it. And so when we get over to C, we would say, oh, that's pointing to something. So we'd come down to this first node, and we'd say traverse our trie from this point on down, but print a C in front of whatever you find. Well, if I treat this as my root, what am I going to find? I'm going to find an A, I'm going to find an AT, and I'm going to find an AB. And I'll print each of those with a C. So we can do recursive traversal, and you just have to, as you're going through, print the prefix before each thing that you find. How do we know which word it is trying to make? We don't really until you get to the end. Basically, anywhere that I find a pointer here, if a pointer in the root means that there's a word stored somewhere in my trie that starts with, say, an M. And let's say that points to a node down here. And let's say there's a non-null pointer at I. Well, there's a word somewhere in the trie that starts with an M followed by an I. And there might be multiple words of that type. So if I find a pointer on the node associated with D, that means there's some words that start with an MID. And at each point, if I find my end of string word flag is set to a 1, then it means whatever letters I've seen up to that point, that's a word in my trie. So in this case, we've got the word MID. No, you can absolutely search. So is there a car? Well, start from a C, that's not null, so there's something that starts with a C. Follow that to another node, here's the A, that's not null, so there's something that starts with a CA. Follow that to another node. Check the R is null, nope, there's no CAR. Is there a cat? Well, check the C, yeah, it comes down here. Is there an A? Yes, come down here. Is there a pointer from T? Yes, there is. See where that goes. Check the end of string flag on that node. It's set to a 1, yeah, we've got a cat. So you can absolutely search in here. And it's an efficient search. It's order the number of letters in your string. trie is only for storing strings. That's usually how we see them, but you can treat anything as a string, right? I could store you know, binary data if I wanted, and my trie would have, you know, two nodes, a 0 and a 1, and that gets into an interesting perspective on things. I could store decimal data if I had a bunch of decimal numbers. I could have 10 nodes, one for each digit, and I could store, you know, phone numbers that way if I wanted. Pretty much anything you can break into this structure. It's a little interesting to notice, though, that there's nowhere in the memory of the computer where the string CAT is stored. Right? If my whole memory was being used to store this trie, I don't even find the ASCII code for C necessarily stored anywhere, or an A or a T, and I definitely don't find those ASCII codes stored one after another. The storage of this information is really in the structure of these pointers, and it's the position of each pointer within each node that really contains the information that we pull out of this, which is the set of characters for each word. And so that's a little funky. So any questions on the trie quiz? All right, cool. Let's see, we've got some time. Any questions or reflections on longest common subsequence? All right, so let's talk about egg dropping. So most engineering schools have at some point some kind of egg drop competition, where usually you're trying to build a device that you can put an egg in and drop it, and the goal is to see whether your device protects the egg properly. So for some reason there's a legacy of egg dropping in engineering. So there's a classic egg drop problem we can talk about in computer science related to dynamic programming. And the setup is, you know, you've got some sort of building, and it's got a number of floors, and you've got a basket of eggs. All right, so let's say you have E eggs and F floors. And your... Whoa, that's cool. Nice. So you have E eggs and F floors. And our goal is to discover what the highest floor is that we can drop an egg from without it breaking. Alright, so we want to find the highest floor from which a dropped egg will survive. And we make all kinds of simplifying assumptions. So all the eggs are identical. If you drop an egg and it survives, it's in exactly the same state as before you dropped it, so there's no successive damage. And if I can drop it from a given floor and it survives, I can drop it from a lower floor and it's guaranteed to survive. So these are idealized eggs in idealized situations. And so this means that we can start conducting experiments. By dropping eggs from different floors, we can see if they break or if they survive, and we can make some hypotheses and test those by running more experiments. And so if you've got a total of E eggs and F floors, the question is, how many experiments does it take to answer this question? And this is, I'm just going to refer to this as the question. Because we're going to have a number of questions, but this is the question. What's the highest floor from which a dropped egg will survive? Yeah, it's a little bit like stick picking. Alright, so there are a number of ways to do this, and we're trying to find what's the smallest number of experiments that we need to run that will guarantee a solution to this question. And we may, you know, start off by dropping one egg from the first floor and it breaks. And we're done. It only took us one experiment and we've got our answer. The highest floor is floor 0, right? There is no floor from which you can drop it safely. But we're not looking for, you know, what might be, you know, the number of experiments we need. We're looking for a guaranteed number. I want to know, I can do, you know, 16 experiments, and after that I can absolutely answer the question, regardless of, you know, what the answer is. And we're looking for what's the best guaranteed number of trials that you need to answer the question. Alright, so the problem setup is critical, and there's you know, maximums and minimums going on here, right? But hopefully that makes sense, right? So you want to be able to give somebody a guarantee, hey, with, you know, 7 experiments I can answer the question. And you want to know that that's the best possible guarantee you can make. There's no way you can guarantee an answer with only 6 experiments, but you can guarantee it with 7. In that case, the answer to the question would be 7, or, you know, the answer to how many experiments it takes. All right. So how do we do this? So let's look at the question, right? So suppose you only had one egg. Okay, how would you figure out the highest floor from which an egg will survive? What would be your procedure? You got a single egg. Drop it from the lowest spot and keep moving up until it breaks. That's the only way you can do this. If I start from the second floor and I drop it and it breaks, I have no eggs left. And I can't find out if it would have survived from the first floor or not. So if you only have one egg, you've got to start from the first floor, move to the second, move to the third, and so on. Right? That's the only way you can do it. And if I have F floors, if I have 5 floors, right, I have to try it from the first, second, third, fourth. I might have to do 5 experiments. I might have to drop it from the 5th floor if it survived the first 4. And then if it survives the 5th, I know my answer is 5. And if it breaks, I know my answer was 4. So if egg is equal to 1, we just return F. That's the number of experiments that we might need. Yeah, we can't go random. All right, if we have only a single floor in our building, how many experiments does it take? It takes just one. It doesn't matter how many eggs we have. If the number of floors is equal to 1, just drop an egg off that first floor, and it'll break or it will not break. So if floors is equal to 1, return 1. And just to make things so we don't have to think too hard, if the number of floors is less than or equal to 0, it doesn't take any experiments. We don't have any experiments to run. So that's just a code simplifying base case. All right, so how are we going to do this in the general case? If you had 2 eggs, right, you could, no negative floors, no inception. If you had 2 eggs, right, you could gamble, you could play high-low with one of them. You could start, the first one in the middle. And if it survives from there, well, you know that your floor is somewhere above that, your critical floor, right? And you've got 2 eggs left to solve that subproblem. If you drop from a floor in the middle and your egg breaks, you've only got 1 egg left, but you've cut your problem in half. So now you could go 1 floor at a time from the first floor up to right before where it broke. Cool, that's a good solution too. So it is a little bit of high-low, but it's a bit of a weird case of high-low. Because of this business that when an egg breaks, you lose it from your tools that you can do experiments with. So if we cut this in the middle and our egg survives, we've got 2 eggs left to explore this half problem. If we drop an egg from the middle and it breaks, we've got 1 egg left to explore this lower half problem, and that one we have to do 1 floor at a time. So, how are we going to do this? It's not an obvious algorithm. But we can define the answer to how many questions does it take, how many experiments does it take. We can define that recursively. So here's our setup. We're going to drop 1 egg. What floor are we going to drop it from? I don't know. It's going to be somewhere between the first floor and the top floor. So let's do this. For test floor equals 1 to F. Alright, so we're going to see what the best solution is if we start off by dropping from floor 1 or floor 2 or floor 3. And when we're done, we'll record whatever our best answer was, right? The fewest number of trials. Alright, so this is the experiment where we drop 1 egg from test floor. And there's 2 possibilities here. Okay. The first possibility is the egg breaks. So we dropped from some floor and the egg broke. Alright, we no longer need to check any floors above that point. So now we have a new question to solve. We have egg minus 1 floors, or egg minus 1 eggs, because we just lost 1. And we have test floor minus 1 floors. So find what the best number of trials is that will guarantee an answer with this setup, and add 1 to that, because we just did an experiment by dropping off of test floor, and that's the total number of trials it takes to answer the question if we start by dropping 1 egg off test floor. So I'm going to call that B for break. The other possibility is the egg survives. So if the egg survives, what's the number of experiments we need to answer the question? Well, one experiment, because we dropped it from test floor, plus, well, we still have E eggs because our egg did not break. And if it survived from this floor, now we need to answer the question on a building with this many floors. Right? We don't need to retest from here, so this is floor 1, 2, 3, and so on. And so that's basically floors minus test floor. So depending on the results of this first experiment, one of these will be the number of trials that it will take total to answer the question. We want to know the smallest guaranteed sufficient number of trials, right? So, so best is going to be the largest of these two, because that guarantees that's guaranteed to be sufficient. And let's start off with, you know, the best. I don't know, we'll initialize it to infinity or something. Initialize it to floors plus 1. Some number that's bigger than what your final answer is going to be. And so if the best scenario, dropping from test floor, if best is less than the best, then set the best equal to best. Come out of your for loop, return the best, and there you go. So it's the same structure where we've got, you know, repeated recursive calls to our function, and we're going to see lots of repetitions of the same cases. And so dynamic programming will speed this up nicely. We'll save the answer for each egg floor combination that we've encountered, and then the next time we look for that combination, we'll pull it out of a cache instead of recalculating it. And this codes pretty easily. Right, so here's our egg function. If eggs is 1, return floors. If floors is not positive, return 0. If floors is 1, return 1. That's our base case. Here's our check for our cached answer. Here's the, I called it the best in my paper, but this is the best number of experiments that we need. And there's our two possibilities. If the egg breaks, then this is how many experiments we needed. If the egg doesn't break, this is how many experiments we need. This is the guaranteed number of experiments to answer the question if we start from floor F. Right, so we take the largest of those two, and if that's better than the best answer we've seen, save it, and then at the end return that, save it in your cache. And so this works. So if you have 5 floors and you have 3 eggs, it takes you 3 drops. If you have 5 floors and you have 2 eggs, it takes you also 3 drops. If you have 15 floors and 3 eggs, it takes you 5 drops. I can post this in the shared area. Yeah, that would be fine. All right, cool. We are out of time. Sorry for the late start. But anyway, we're going to go back talking about trees on Monday. Sorry, Monday is your SLP. So I posted an announcement with the Zoom info for the SLP. I will not be in the regular classroom. I'll be on that Zoom location. So show up 10 o'clock for the SLP presentation. And then Tuesday we'll go ahead and we'll start talking about trees some more. All right, cool. Have a good one. Talk to you next time.